The standard approach to enterprise AI has been to push massive, dense, large language models into production. These models process their entire massive parameter count for every single word they generate. It takes tremendous computing power. When a company scales that up to millions of users, spinning up an entire neural network for a simple query exhausts servers and drains budgets. The industry's proposed fix is the mixture of experts architecture. Instead of waking up the whole system, an MoE model acts like a smart router. It takes a prompt and only sends it to a few specialized neural pathways, leaving the rest of the model dormant. The theory sounds perfect on a whiteboard, but building infrastructure requires real numbers. We have to measure exactly what happens when these models hit actual production servers. You cannot budget for enterprise software by relying on vague marketing claims or static pricing pages. You have to measure the live latency and the actual API receipts. To get those numbers, we are using the MoE Cost Analyzer. Every line of code for this tool was written and evaluated completely autonomously by an AI engineering agent named Neo. It skips local simulations entirely. It takes real-world prompts and fires them through open internet APIs to record the exact response times and billing data. We are stripping away the AI mysticism to look at the raw, mathematical reality of how these models behave under live load. We took 100 live sentiment analysis tasks and pushed them through the OpenRouter API, sending them down two identical pipelines, a standard dense model and its MoE counterpart. We set strict boundaries, latency under 3,000 milliseconds, and cost under 2 cents per 1,000 queries. When an architecture is designed to run faster, the immediate concern is that it's taking shortcuts and spitting out shorter, less detailed answers. Across the 100 tasks, the dense model generated exactly 4,939 total tokens. The MoE model also generated exactly 4,939 total tokens. The structural output is perfectly identical. Any speed or cost improvements are strictly the result of a more efficient system, not a drop in quality. Looking at the billing data, the MoE model dropped the total cost by exactly 20%. Active parameters per token drop significantly. The routing system leaves most of the network dormant, using a fraction of the power. Latency distribution shows a 27.3% faster P50 median load. Even at the P95 tail under heavy traffic, MoE remains faster. Under that intense network stress, both models drag. The MoE model is still faster, but the speed advantage shrinks down to 12.9%. That squeeze tells us this is a grounded, realistic snapshot of open internet infrastructure. It captures the actual friction of a live production environment. Saving 20% on a small 100-query benchmark amounts to fractions of a penny. This graph projects those metrics over scale. When you apply that 20% gap to 100 million daily queries, the lines diverge rapidly. The math snowballs. You save nearly $3,000 every month on API costs, while simultaneously eliminating thousands of cumulative hours of loading time for your users. Choosing the right architectural efficiency directly translates to major capital preservation and a completely frictionless user experience. The analyzer's final terminal output recorded 0 API errors, cleared both time and budget SLAs, and gave a definitive green light: use MoE. That specific recommendation is mathematically locked in for this dataset, but the larger lesson is the measurement methodology itself. Your product relies on unique prompts, distinct traffic patterns, and unique user demands. You cannot build a reliable type stack by trusting generalized industry white papers. The modern AI landscape moves too fast for assumptions. To win, discard the hype, pick up empirical tools, and test your own specific workloads.